Okay, we want to talk about integrating over region. It's not a rectangular region. We've seen how to integrate over rectangular region, straightforward enough. Okay, we have a region bounded by two graphs. Yeah, let's say that we have a function y equals f1 of x and another graph y equals f2 of x. Provided we can find the point of intersection between the two curves, we can set up an integral in a way very similar to what we did previously. So we think, okay, here's the x coordinate of one intersection point, here's the x coordinate of another, of the other. Okay, and here's the region we want to integrate over. Okay, and let's just say we want to find the area of this region. That's the simplest thing to integrate. Okay, so what we do is we partition the interval from A to B in the usual manner, what we did previously. So we have a typical interval. Okay, so here's the interval of x pi minus 1, x sub I, with a sample point somewhere within that interval, doesn't matter where. The reason it doesn't matter where is we're going to let these intervals shrink down to 0 or approach 0 so that there becomes less and less choice of where this thing, where the sample point lies within the interval. As the endpoints of the interval approach each other, this thing is constrained more and more closely, and everything works out in a way that we'll see. And so if we draw a couple dotted lines to indicate the vertical strip corresponding to this interval, we can then draw the region that we want to approximate. So this region is going to be approximated by a region that a rectangular region. And we take our sample point and we determine the y coordinate of the sample point. So here the y coordinate would be y equals f2 of xi star. Up there, the y coordinate would be f1 of xi star. So now we've got this strip here that's approximated I'll draw a little bit of a picture of it over here. Okay, this is your ith strip. The width is delta x sub I equals x sub I minus x sub I minus 1. And the interval goes here from y equals f1 of x I star to y equals that's actually y equals f2 of x I star to y equals f1 of x I. Now, if we were looking for the area, well, we could get the area of that strip in a very straightforward manner. Okay? We just multiply delta xi by the difference between these two. And we see that the area is the length times the width. The length is just f of it, f1 of xi star minus f2 of xi star. Multiplied by delta xi star. So the total area, oh, it's got a hard place on it, so we're gonna write with it though. Now, when I say we partition a sub I, the interval a b, let's go ahead and write out the partition. It's probably a good idea to do that. A equals x naught, which is less than x1, which is less than dot 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 up to x I minus 1, less than x I, just to pick out a typical interval, less than x sub n equals b. Total area, that is going to be the sum from I equals 1 to n of the areas of these strips. So it'll be the sum from I equals 1 to n of f of x I star f1 of xi star minus f2 of xi star multiplied by delta xi star. Well, it turns out that's just the integral from A to B of f1 of x minus f2 of x ds. So the area integral is pretty straightforward. What if, though, we have some function? I use f for these two functions. So let's say we have now a function g of x1 that lies above this region. And we want to find the volume between the graph of that g of xy and this region here. Well, just decide that we'll keep it there for reference. And I guess we'll move the camera. I'm used to this fancy new camera. Maybe I'm moving in the right direction. Yeah, that's right. Okay, so we'll do there. Also, I apologize. I keep forgetting about the watermark. So what I wrote down here, make sure we got it. It tends to get lost in the watermark, and I can't seem to get zoomed out to make. I've got a little banner here. So, if you were trying to see this, maybe you weren't able to see what I wrote here, but there it is. Okay. And this is pretty straightforward. Let's get out. Let's follow. Well, we've illustrated this, and I might illustrate it in 3 dimensions, but if you go back to what we did previously, the picture looks a whole lot the same, except that the regions aren't rectangular. In this case, after we do our partitioning and so forth, and I'm sorry, I'm getting used to this camera. What I have to do. Sure. Well, I've got the camera back on this picture again. Of course, now over here we've got new board. Okay. Okay, so we have our region. Just to review, looks something like this. We've partitioned the X interval, and we understand that we get strips in the Y direction. For each Y strip, we can partition that strip. So let's take our ith strip again. Again, Y goes from F2 of Xi star to F1 of Xi star. And then we partition the interval. Okay. We get okay, now I'm going to have to use 2 subscripts. I didn't before because we had a rectangular region with sides parallel to the coordinate axis. Over here, I started my partition with here. Okay, partitioning this, I'm partitioning the I strip, where I is the index that we use for the X partition. Since the values of F2 of xi star and F1 of xi star are typically going to be different for two different strips, then we want to index this partition by the number of the strip that were subpartitioned. Okay, we've got to partition the region into n strips. Now each strip we want to partition into y energy. Each strip has bounds on the y coordinate. Okay, so when we index this partition, we're indexing the ith strip, so we're going to use I in the partition. So we're going to use two numbers down here to indicate which region we have in the partition. And of course, what we're going to get when we do that is we're going to have divided this ith strip into a bunch of smaller rings. And on every one of these intervals, the value of our function g of xy is going to be relatively constant. It's not going to change drastically. And that's the key. And hopefully understand that from what we did previously. So we have this partition, and I'm going to just write out the rest of it. And that's what it is. Myself enough room over here. I think we've got all that. Did we get all that in the screen? So just a little more. Okay. Leave myself enough room over here. But the typical interval will then be increment here. Will be y sub I j minus 1. I used a comma here to indicate we only have two numbers, I and j minus 1. Otherwise, you might read it as three numbers, I, j, negative 1. Okay, so we have I, j minus 1. Then we have y, I, j. Then up to y, I, m. And we use m, n and m for the maximum indices in our previous partition, the rectangle. But since we're partitioning the ith interval, the number of y intervals that we get won't necessarily be the same for every strip. So we're going to use m sub I for the number of subintervals in the ith strip. So one strip can have a different number of subintervals than another. Okay, so there's our partition. So now we're going to have a typical increment up here. Here's your IJ increment. If we enlarge the IJ increment, we have x equals xi minus 1, x equals xi. And we have our delta S sub I as before. And then we have y equals yij minus 1 here. Y equals yij here. And of course, we have a delta y ij. We still have our sample point at coordinate x equals xi star. We'll also have a yij star. Then the value of our function at this point is, of course, g of xi star yij star. Put myself in label this the volume above. I want to write the word increment, say the volume above this thing, is then going to be approximately the altitude, which is your g value, times your delta xi, delta yi. The total volume is a sum from I equals 1 m I equals 1 to m of the sum. Let me back up. Here, so I'm gonna I want to do total volume. I want to do the volume of the pipe strip. And that's just going to be the sum from j equals 1 to m sub I, because of course a partition takes us from j equals 0 to j equals I m sub I. And this expression. I could give this a symbol, but not like the total volume down here. Okay, the total volume, we just sum this from I equals 1 to n. My indices there. And so what's our total volume? Here's the watermark walking up there. It's got to be the sum all from the strips there are n strips, all right, from I equal 1 to n of the sum from j equals 1 to m sub I of g of xi star yij star delta xi delta yj. So there's our main picture. Now we have to approach an interval. We have to get an interval out of this. We're going to get an interval out of this. So I'm going to write it up here. The sum from I equals 1 to n, the sum from j equals 1 to n sub I, u of xi star, yij star, I delta yj, yij, I have I in the yij. Approaches in the limit. I'm being a little vague about what limit we're taking, but it's a limit as delta xi's and delta yij's all go to 0. The integral. First of all, from A to B, because of course our strips go from A to B, if you recall the original picture. We partition our region A to B, and we get strips. So we have a whole series of strips there. So, let's see. We have a bunch of rectangles, and each of which we've partitioned in the y direction. And that gives us something that we can visualize looks like this. We take the typical increment in the ith strip, we take the jth increment in the y direction, enlarge it, and here are some of the dimensions. It's easy to write down what the area is, and not difficult to write down what the total volume is above these rectangles, as approximated by the values of G at the sample point in each of the strips, each of the rectangular entities, small rectangular entities. Now this sum using standard technique. Goes from A to B, and we're going to be integrating e of x, y with respect to x and with respect to y. I don't yet have limits here. What are the limits? And I've got that back. Integrating with respect to y and then respect to x. Okay. What are the limits on my y interval? Well, you recall that each y strip goes from f2 of xi star to f1 of xi star. It follows. Okay, so I go from f2 of x to f1 of x. Now, as you know, because you've already done some integrals, what we're trying to do is clarify what you've done when you've done the integrals, so you learn how to set up integrals so that you'll understand what's coming in the next month. And what's coming is the main focus of the vector calculus course, at least one of the two main foci. Okay, which is the integral theorem, Stokes theorem, Lagrange theorem, and so forth. Okay. Here's, so again, you can visualize this region as in terms of what happens to given value of x, say for given xi star, y goes from what? F2 of x to F1. And if you know the limits on y for given x, and that's straightforward in the case of two functions here, then you basically got your integral. But you want to understand this integral as the limit of sums in the way that we've developed it. Well, that's particularly easy when you have two functions. The region is described geometrically or in some other way. It's not always quite as easy, but it comes down to, again, answering the question for given x, what are the limits on y? I'll also comment just briefly, we'll get into more detail. So let's say the function, let's say the region looks like this. I could also partition the region on y. Okay, y goes from here to here. But that gets a little bit complicated. If y is here, then the limits go from, and of course, if we partition y first, then we're talking about strips in the y direction. Now, sometimes it's easier to do that. Sometimes it's easier to do that than it is to do the x direction. Can I say that right? Yeah. If you fix y here, you get a strip in the x direction. In this case, the strip goes from the value of f2 or f1 to the value of f2. However, if y is up here, you see that this strip goes from a point of the F1 graph to another point of the F1 graph. And down here, we have a similar situation where Y goes from, or X goes from a point of the F1 graph to a point on the F1. This is the F1 graph. So here for given Y, X goes from a point on the F1 graph to a point on the F1 graph. Down here, for this Y, X would go from a point on the F2 graph to a point on the F2 graph. And here it goes from a point on the F1 graph to a point on the F2 graph. Okay, that gets a little bit complicated because you have to set up an integral from each case. So, well, we're going to look at that.